Hey guys, on today's episode, we have ballistic engineer Jeff Siewert back on the show. Now we cover a bunch of topics about precision rifles. We start off talking about gain twist barrels. We then move into muzzle devices, muzzle tuners, muzzle brakes. Then we take a dive into propellants, and then we look at drag variability and some different ways you can control that. We think you'll enjoy this educational episode.
I'm Joyce Hornady. You might say accuracy is my business. I make bullets.
You are listening to the Hornady Podcast.
Thanks for joining us and enjoy the show.
Hey guys, thanks for tuning in to this episode of the Hornady Podcast. I'm your host, Seth, and today I've got to my left, in the corner, Senior Ballistician Jayden Quinlan. Jayden, thanks for coming on the show.
You bet.
Yep. Not necessarily a Quinlan's Corner episode, although we do put you in the corner.
Yeah.
So you can join me in welcoming special guest, author, scientist, all-around ballistic guru, Jeff Siewert. Jeff, thanks for coming back on.
Thanks for having me again.
Yeah, absolutely. We enjoy having you. And, being here in a flyover state or a drive-through state, as it were, it's been really nice to have consistent Jeff Siewert appearances just in your travels.
I keep inviting myself, and you guys never say no. So
yeah. Well, you've given your life to a career in ballistics, and so when you do something for a job, maybe, one, it might be hard to let go, but two, sometimes you just don't want to do that anymore.
I'm still really passionate about it. So I'm happy to contribute where I can, and hopefully there'll be some things today that open some eyes and get people thinking a little bit differently than they have been in the past.
And I think that really sums up all of the episodes that you've been on the Hornady Podcast. Anytime we've had Jeff on, he always gives that insight, that technical, really scientific, and then valid and tested thought process. And I know from the comments and from people reaching out, we go to these trade shows where you interact with the end users, and there's been a lot of copies of Ammunition Demystified sold because they saw it on the Hornady Podcast. They heard how well you can articulate this super complex stuff down to, an advanced hobbyist level. And Ammunition Demystified, the non-Bubba's guide to ammo and how it really works. That's Jeff's book. If you haven't yet, check that out. It's on Amazon. It's a read-through book that could also serve as a textbook. That's the best way I can summarize it. So,
yep, I still reference it weekly sometimes. Depending on what I'm working on. Absolutely.
Well, it's great. You can have a pocket version of Jeff.
Yeah.
You think, oh gosh, that's a question for Jeff. Where Jeff, being one of your mentors in the world of ballistics, has always been the go-to guy. If we're stumped here at Hornady, well, now you got a pocket version.
Yeah, I do have his cell phone. So if I'm feeling real lazy, I just call him.
Fair enough. Well, listener out there, you too can have your own pocket ballistician, Jeff Siewert. Grab a copy of Ammunition Demystified. Today's topics, Jeff, you did a great job of just supplying us. Hey, we've talked about some of these topics in the past, and let's expand on them just a little bit more. Let's go into just that little bit more, just past the click of information. And so we're going to bounce around topics a little bit, but they're all going to be, if you're a long-range precision shooter, if you're looking for accuracy at range, if you're in the game of, really high-performance rifles, this will be a very interesting podcast for you. And we're going to start with something that I know very little about and something that I've no experience with outside of firing some test shots for pressure and velocity in the lab. Outside of that, I have no experience with gain twist. And so I'm going to assume there's a lot of listeners with very little knowledge about gain twist. So let's start at base level, Jeff. What is a gain twist? What are we trying to achieve with that?
Well, so gain twist is an approach you typically employed by medium caliber ammunition. And the idea is that if the barrel that the ammunition is being fired in has some forcing cone erosion, can you make the barrel more tolerant of erosion and still obtain the sort of performance that you were shooting for? And with a gain twist, you can start at a lower initial twist angle, not strip the band off, and exit the barrel with full spin. Like, okay, that's a desirable goal.
Mm-hmm.
And medium cal, it's ubiquitous. It's everywhere.
Okay, it's the standard.
It is the standard. Small cal typically doesn't get used. It's hard to make. You can't make button rifle barrels with a gain twist. You can't make hammer forge barrels with a gain twist. So those systems tend to not use it unless you've got single point or a broach stack to cut the rifling with. And like, okay. And the problem is that with fixed ammunition where the bullet is crimped to the cartridge case, usually those are loaded to a standard length, and whatever erosion is in the forcing cone is kind of what's there. And the bullet exits the case with no initial spin. And then as soon as you start to engrave, there's a torque spike that occurs just as the bullet starts to engage the rifling. And the farther down barrel the erosion is, the bigger that torque spike is. So you can get in trouble pretty quickly with constant twist. And that's the primary reason why they migrated away from that in medium caliber.
Okay, because in small cal, the constant twist rate, you order a barrel 1 in 8 twist, it's 1 in 8 from front to back.
That's correct.
That's the standard for small cal.
That's correct. So up on the graph here, what we have is constant twist in the black line, what I'm calling an intermediate parabolic gain in the yellow, a full parabolic gain in the red, and a thing called sinusoidal.
Yeah, now they'll have to define those. I know the shape parabolic. So how does that apply to rifling? I know obviously the sinusoidal reference.
Yeah, so the equation you use to generate the twist rate is a parabolic equation.
Okay.
And you can start it anywhere. So that's why there's a full gain, a full parabolic gain, and an intermediate parabolic gain.
Gotcha. Okay.
So these guys don't start at the constant twist angle, whatever that angle happens to be. There's always some initial startup at 0 twist, and then it clicks over, and the bullet engages the rifling and then starts to spin up. Okay. The sinusoidal is like, we start it real easy, and then we torque up, and then we back off at muzzle exit. And it's important to have low torque at muzzle exit because that induces an angular rate, a wobble of the bullet. And so you don't want to exit with a large amount of torque left on the bullet.
That makes sense.
Okay. So on the next slide here, we've got the torque versus travel for the different rifling twists. And this is the constant twist, and that follows the pressure time curve.
Right.
And it's the pressure time on the base of the bullet, not the chamber. So as bullets gain in velocity, there's an increasing difference in pressure operating in the chamber versus the base of the bullet. The faster the bullet, the bigger the gradient.
Okay. And that's interesting that, I didn't necessarily anticipate that, where the constant twist would have the lowest torque.
Yep. So
as it travels.
Yeah. So here you see this little jiggity jog in the torque versus travel. And that jiggity jog is the bullet engaging the rifling after the free run from being released from the cartridge case. Okay. So the intermediate parabolic is something that you might think about using if you were a competitive shooter. Okay. Full parabolic, typically we stay away from that because the downside to using the full parabolic is the fact that the rifling angle changes as much as it possibly can. It goes from 0 to the exit twist, and you're moving more material on the jacket of the bullet. So not a big problem for medium and large cal bullets, serious trouble
for small cal.
For a small cal.
When you look, if you calculated the area that's underneath that curve compared to the other two that we've talked about already, just the overall torque that it experiences under there is significantly larger.
Yep. And the one that we always stay away from even though it sounds like a good idea, is the sinusoidal.
Okay.
That, I mean, gives you more peak torque. You have high torque at exit. I mean, there's a lot of reasons to stay away from that. So the whole deal with gain twist is it's a solution to accommodate, at least in medium cal, severely worn forcing cones.
Okay.
In service barrels. So that's really why that's used.
Yeah. So just based on this graph, you said the intermediate parabolic gain would be one that you would consider. So an example of that would be you want to exit with an 8 twist. Maybe you start with something like a 12 or a 10.
Or something like that.
Okay.
Yep. So that, and the general design rules are you keep it constant until you hit the travel at peak pressure. And then you do whatever gain function mathematically that you have selected.
Mm-hmm.
And then a couple of calibers before muzzle exit, you revert back to whatever your exit twist is.
Okay.
Yeah. Jeff, can you talk? I'm sure the listener is going to think, so this doesn't have the depth of testing in small cal as it does to medium cal. So why are you more concerned with making sure that you get the bullet spun up with medium cal and is more sensitive to the throat erosion compared to small cal?
Thanks for the question. Medium cal, you have a small defined portion of the bullet called a rotating band, and that's what engages the rifling. None of the rest of the bullet touches the bottom of the grooves.
Okay.
So that's the thing that engages the rifling and provides the torque to the bullet. And because the stresses are concentrated, you get considerably more wear with those than you would with let's just talk off the top of my head here. Let's talk percent band worn for different caliber bullets. Look, so for a 50 caliber bullet, you might exit with 1% worn. Tiny fraction. Smaller calibers might be less than that. Medium caliber bullet, plastic rotating bands used on the GAU 8, typical number was about 35%.
Oh, wow. So significantly more.
Very, and that's in a brand new barrel. So you really have to be able to tolerate a larger percent worn and do it smartly.
Yeah. Well, in that example, it's clear to see why in medium cal it is the standard versus small cal. We're talking super small numbers, largely imperceivable, I would assume. So I could see why small cal gain twist just hasn't really caught on. And I could also see why there'd be a tendency if you know this information about small cal, well, why wouldn't it also apply, medium cal, why would it not also supply to my precision rifle?
Yeah, so the dispersion on small cal systems can be related to an effective in-bore clearance. How much can the bullet tip relative to the bore centerline? The numbers are already pretty doggone small with constant twist. How much can you fix it by applying a gain twist? And the answer is there's not a lot of up available.
Yeah.
You don't have that ability. Now, different applications, say a machine gun. Could you use a gain twist in a small cal machine gun? Absolutely. And it might be beneficial.
Yeah. In your experience and in your testing and in your balloting examples, for small cal, would you think there's any marked advantage of going with a intermediate parabolic gain twist?
Concealed carry, personal protection, or home defense. Only the best will do. Critical defense ammunition, developed to provide the best performance for personal protection, no matter what platform you choose. Delivering consistent, reliable performance. Every single time. When lives are on the line, only the best will do. Hornady Critical Defense Ammunition.
I'm going to reserve judgment on that.
Okay.
I think there might be, but I think you're going to have to be right at the kind of the cutting edge of dispersion. You really, Once all of the other boxes are checked, let's try that one.
Yeah. Well, I personally, gosh, Jayden, it was probably, 6 years ago, maybe 5 years ago? Nobody ran a gain twist, and then all of a sudden, I got to get a left-hand gain twist for my next precision rifle. And, it cost extra. You're in longer lead times. And then those guys are still, not all of them, but in this example, it's like you've got a guy that's a mid-pack shooter. And, this next one, I'm going to go with the gain twist. Well, he's still a mid-pack shooter.
Right.
So I felt like there was this surge in popularity that I'm not sure what spiked that. And then it kind of really quickly was a flash in the pan. And now you see most top-level competitors, certainly our sponsored guys that are top-level competitors, they're running constant twist barrels.
Yeah. Well, the other thing that you can have happen with a gain twist is the torque impulse of the recoil that you feel when shooting the rifle is lengthened. You would perceive it as being less. So when you, let's say, a lot of shooters will have, a bipod that has cant built into it, right? And you have your little swivel lock real loose, and you fire a shot, and generally we're shooting right twist barrels for the majority of use cases. You can feel the rifle cant to the right. And the faster the twist rate is, the faster the bullets go and the heavier the bullet is, all of that stuff included, you can feel quite a bit of rifle cant with certain applications.
It torques in your wrist, you can feel it.
Yeah, a gain twist will take that torque and spread it out over time a little bit, which is essentially what Jeff is showing in these graphs that you see right there, where the black line, you see an immediately peak in the torque, and then it starts to trail back off. That's the constant twist rate. As soon as the bullet hits that rifling, it's immediately being spun up to that full twist rate, where these other ones, where you have the gain, you're slowly reaching that same level of twist rate over time. So that's why you feel the difference there.
Got it. Yeah, which, that at the elite levels of competition, like Jeff, like you mentioned, when you've got all the boxes checked and you're at the pinnacle of performance and dispersion, maybe that small little difference in perceived torque in the gun is enough to make the difference, regardless of what it does to your dispersion and muzzle exit condition, just in you running the gun. If that helps you, maybe that's worthwhile.
And I'm just having a thought here that it may have the potential to help reduce the magnitude on some flyers. But I now I got to make a note and do some more studies.
Okay. That's great stuff. We'll love to have you for a part 2.
Okay.
So gain twist, are you ready to move on topics?
I'm ready to move on.
Anything else on gain twist barrels?
I don't think so. I just wanted to ask that kind of question, Jeff, because I think a lot of users will wonder, because it sounds like there's some definite advantages to be had here in certain regards, and why hasn't it happened? There's nothing new under the sun kind of thing. Why hasn't it happened? And I think that's an important distinction, that in the medium or large cal world, with those differences in the driving band configuration compared to small cal, that's a necessity. I mean, when you have problems in the medium and large cal world because of throat erosion like that, you're talking catastrophic performance problems.
Right.
So the avoidance of that with the gain twist is, it's like a go, no go, right? Either this thing's going to work or it's not type of thing, where in small cal, we're talking about maybe minuscule levels of performance advantage. It's not a catastrophic, the bullet's going to spin up completely or not problem, which is what it is in medium and large cal.
So I did a job on the M240 with a gain twist barrel a few years back, more than a few years back now. And the plug that you use to check throat erosion was, pretty far down the barrel. And so, you make the numbers and you say, okay, the bullet doesn't spin until you get to that no-go plug erosion depth. You're a long way down the tube. The torque spike's gigantic.
Yep.
Can you fix it with using a gain twist? Yeah, you probably can.
Right.
Interesting.
So there you are.
Yeah, there we go. So
hopefully that answers the questions about gain twist.
Yeah, that there may be a small advantage, and I'm guessing all the barrel makers are using an intermediate parabolic gain. Most of them are starting somewhat, I'm going to call it reasonable. You don't see 14 to 7. You usually see 10 and a quarter to 9 or something along those lines. You don't see anything too crazy there. So
in the balloting code that we discussed previously, and we're going to discuss a little bit later today, I have the capability to put in the gain twist function and see what effect that has on the dynamic motion of the bullet in the tube. So now I got to go study.
Now you got to know. Well, also a good point to ask the listener, the viewer, if you have questions regarding gain twist or its advantages or disadvantages, drop them in the comments. If you have more studying to do, Jeff, in this regard, we can get some comments, some questions pulled out of the comments and submitted to you to help, make that study a little bit more worth your time. So with that, shifting gears from the alleged gains of a gain twist, switching over to propellant, right?
We're gonna cover, I think, briefly a little follow up on the muzzle tuner.
Oh yeah,
and the whole one of the things that we didn't really broach in that discussion was tuner versus. Well, we did talk about it a little bit, and that's why I wanted Miles here. But here we go.
Yeah.
Yeah, so there's a difference between the effect of a muzzle tuner versus a muzzle brake or suppressor.
Absolutely.
And yes, there's added mass with all of them, but the thing that the muzzle brake and or suppressor bring to the party is the ability to strip the gas around the back of the bullet as the bullet exits the tube.
Okay.
So this picture that I'm showing here, this is a test bed vehicle from about 40 years ago. We got a contract to do fuse development. We had to develop a test bed vehicle that would fly reasonably well and give us the ability to test the fuse function. Well, part of the things that we did was we lengthened the fin and we did a little sweep back here. And we had T-pad cross-section on the fins. And the T-pad, some folks would say, oh, that's a bore rider. It's a little T-shaped thing at the top of the fin that is closest to the bore. And we got these, it's called the smear camera image. They do flight followers these days. But basically what happens, the film runs by in the opposite direction of a narrow slit as the bullet runs by in the opposite direction, and you get an image in time of this bullet that is just exited the tube. Well, it's kind of a neat idea. So we got pictures of that test vehicle, and we got parts back from the test, and the fins are all broken at the back end. And they're all jagged. Oh, it must have hit base first. I don't think so. So I had just completed a continuing ed class on strength of materials up at the local university, and I said, well, I can make some numbers. I can figure out what that pressure delta has to be to break these fins off. And it's only about 2,000 PSI. It's not a big number. And you compare that to what are the base pressures that exit from an interior ballistic simulation, you got plenty of capability to break those things there. So okay. So then what we said was, all right, we're gonna chop down the area of the T-pads. And we'll go out and we fire it again. Successful. And we said, okay, we're going to incorporate those changes. So we built another batch of fins, and the changes that we tested didn't get translated properly into the go-forward drawing dimensions. And we fired another batch, and we got fins back that were cracked and almost broken, but not quite. So with that data, we were able to kind of isolate the fact that pressure delta, now this is an expanding bubble of gas that the bullet has to fly through. Mm-hmm. About 2,000 PSI on a gun that had about 8,000 PSI base pressure at exit. So it's about a quarter of what the base pressure is. It's still a lot, and it can do some bad things to the bullet.
Yeah.
And the bad things are shown here.
Yeah, I was going to say that's a great example as following you along through that gas that's essentially going faster than the bullet, once it uncorks, can wreak havoc. Now, in a finned object, obviously it can break fins, but what about small cal?
For spin stabilized bullets, the situation's as bad.
Okay.
Not quite as bad, but almost as bad.
Okay.
So here's a plot of one of our favorite bullets, and what we
got a red tip in it. I like it.
How about that? I did that special for you guys.
All right, thank you.
So here's a plot of the angle of attack generated. Now we had some pretty sophisticated trajectory codes when I was working, and you could put in fixed amount of impulse anywhere along the length of the projectile. And we discovered pretty quickly that if you put the impulse in for half a revolution, you maximize the effect in terms of trajectory disturbance. Okay, so if you put it in more than 180 degrees, you start taking away what you put in earlier. Okay,
yeah,
that makes sense. So anyway, if you change where you put in the impulse, you minimize the angle of attack that the bullet sees. How much above the velocity vector the nose of the bullet points. You minimize that if you put the impulse in at the projectile center of mass, center of gravity. Okay, no big surprise. The next question becomes, where on the bullet do you put in the impulse to minimize the flight path deviation? That's a different metric. So to do that, you minimize the effect on the bullet trajectory by putting the externally applied load in at the normal force center of pressure. That's usually forward of the bullet. The other side of that coin is where would you put the load to maximize the effect on the bullet? And the answer is the back end. So if you want the bullet to shoot small groups, you want to get that base pressure at exit as small as possible. Or, having failed that, strip it away as quickly as possible. So in a 30 cal 308 system, that bubble, you're in reverse flow for about 6 inches of travel. So if you have a muzzle brake or a suppressor and you can strip that gas early, you can probably help yourself out.
That's interesting. So two things that jump out to me there. Number one, if Wish Miles was here, because we did a whole podcast about tuners. Listeners out there, go check that one out. And we touched on it briefly, but we didn't really talk about the muzzle brake. Yes, it's a weight, so there's a tuning effect from just it physically weighing something. But stripping the gas is important. The first thing that comes to mind, though, in regard to Miles Miles has done huge amounts of testing, literal rifle barrels worth of testing for dispersion. And one of the go-to, if you want that thing to shoot smaller groups, drop your powder charge. So I'm guessing, I don't know this, but you're dropping the powder charge, it's going to lower your muzzle exit pressure.
It will do that. The other thing that, of course, happens is you reduce the acceleration. So if there's any sort of plastic deformation that goes on with the bullet as it makes its way through the forcing cone into the barrel, you've reduced that factor, and then you've also reduced the interaction of the bullet with the barrel as a result. So there's a lot going on there when you cut the charge weight.
Yeah, but if you're saying less muzzle exit pressure is helpful, it is checking that box. That's pretty cool. The other thing is muzzle brakes. We use them often in the precision rifle world simply for recoil mitigation. We're shooting rifles that don't recoil anyway, but you want to watch that shot. And if your target's 400 yards away, you want to see the bullet in the air between here and there. Right. And those muzzle brakes help. But you're saying likely, there's a handful of muzzle brakes that everybody uses.
Yep.
And then there's a litany of muzzle brakes that nobody uses. And I'm guessing that's kind of a self-satisfying problem where, hey, this is the brake I use. I shoot small groups. This is so the next guy uses that brake. And so not only is it a recoil mitigation thing, but it could potentially reduce your dispersion.
And I think there's a lot of science that goes on, and I don't have a whole lot of firsthand knowledge, but it occurs to me that, you know, the holes in the brake or suppressor need to be concentric with the extension of the bore. And if they're not, now you've got flow differentials one side to the other. Does the bullet tip? Does that tip the bullet? Does it aggravate any bullet tip that was left over at muzzle exit? I mean, there's a whole lot of things that you need to be mindful of.
Yeah, if you're gonna rob the gases off, attempting to reduce the time spent at the pressure that it's spent at. So if it's full muzzle exit pressure, if you're trying to reduce that by capturing some of those gases and rerouting them away from the bullet, you can do it right and it might have an improvement, but you can also do it wrong and make a whole lot of things worse.
And I have data that talks to that. And yeah, and if you look at a given set of conditions, you know, like there was this particular test had 15 barrels, three different twist rates, different rifling geometries, blah, blah, blah. Any one particular, and they fired a big pile of bullets. It was crowding 200 shots.
You didn't shoot 3-shot groups? No, sorry. Bad joke.
Hey, groups aren't too small. T-shirts are coming, by the way.
So they fired crowding 200 shots, and for any individual rifle, with and without the suppressor, there was no statistically significant difference for any one rifle. But if you look at the whole batch of them, it's different at 95% confidence level. Okay, so yeah, there's something about that particular suppressor with that particular rifle and that bullet. Mm-hmm. We'll talk more about that in a minute.
Okay.
Well, we see that in drag as well, bullet drag.
Oh, sure.
Absolutely. That's why like in the Ford Off, you have the axial form factor adjustment, because we test through as many different configurations as we can, but we don't know which specific one you're using. And it's that unique combination of components you have, barrel, bullet, powder, muzzle, device, that will influence the drag in a specific way.
And when you guys first implemented the Ford Off, I know you caught some flack from some people about the ability to change the form factor.
Right.
That there is a change, despite what everybody wants to believe, barrel to barrel to barrel, and it's just part of the deal.
Yep,
it's part of. I mean, like, there's no way to avoid it. So you have to have that capability in the Ford Off to be able to get stuff to line up.
Yep. Well, and I've been really impressed with, and kind of not taken aback, but seeing some of your test results where you have a muzzle device that, you know, it changes the drag this much, but if that muzzle device is then integrated into a suppressor, then it changes the drag a different amount,
That's
and sometimes in opposite directions. Brake only, drag goes up significantly. Put the suppressor on her, drag comes right back to where it should be. That's been kind of interesting to see.
Now you got me wanting to see that data.
Yeah, right.
Okay, so this is a follow up from the Muzzle Tuner podcast, and we got no muzzle tuner, half sine wave, inverted half sine wave. No muzzle tuners down here. The muzzle tuner plots are up here, and the thing to point out, and again, these bore profiles, they're benign half sine wave things with very small bore deviations.
Okay, they're,
in my opinion, they're
best
small.
case.
Yeah, very small bore deviations. And so for kind of up until you get to the point where it's, 3.5, 4 10,000ths of an inch, kind of can't tell the difference among them.
Right.
You can't do it. Once things get worse, now you can start to pick the stuff out of the pepper.
Yeah. So you're saying, if I'm reading this graph correctly, that the dispersion gets larger with how crooked your barrel is. And to kind of summarize a lot of that podcast was, if your barrel's crooked, there is, you hang a weight at the end of it that brings it back to strength.
It's going to change things, but long term, we need to have a look at the whole picture. The other thing here is, this study was done with these nice benign bore shapes, and all of the barrels that I've looked at over the years, there aren't any nice benign bore shapes. They're always pretty ugly.
Right. Yeah, they're not like the perfect little
nice smooth sine wave curve. It just doesn't happen.
Right.
Just doesn't happen.
But in this example, no matter what you did, the dispersion got worse.
Yep.
Every time you put something on the muzzle, it got worse.
True.
That's interesting.
True. And now, just remember, that's weight alone.
Weight alone, right. Yeah,
that's weight alone.
That's regardless of...
You're not playing with muzzle exit gas at all.
Right.
No, yeah, because you could,
right.
Like you said, divert the gas, shorten the distances traveling in that bubble.
You can have access to the Hornady Handbook of Cartridge Reloading at your fingertips wherever you are, with the Hornady Reloading Guide app available for iPhone and Android. Check it out today.
Yeah. So now let's get to the propellant.
Yeah, this one is really, more voodoo than anything, because the tuners, the muzzle devices, gain twist, that's like a mechanical thing. I can go to a store, I can buy it, I can test it. With propellant, yes, you can do the same thing, but you don't know why it's working. And then you have to shoot significant samples to get valid data. But I find it really fascinating in our sports, obviously the PRS, NRL Hunter, but F-Class, bench rest, all those stuff. 2019, I think it was, for whatever reason, we downloaded the top 20 shooters at the national championships for the short range bench rest. Every single top 20 competitor used the same propellant. Every one of them.
That's by random chance.
Yeah, right. So, and then also when you look at our sport, for example, if you can use Varget, everyone's using Varget. If your case use 4350, everyone's using 4350. You look at F-Class and bench rest. If your case allows you to use a 4831, they're using 4831. Like, there's just some staples on a lot of Vitivori propellants in the competitive space as well. It's just been unique that it's kind of one of those self-satisfying things. Oh, you shoot a 6 or GT and you use 32 grains of Varget? Well, that's what I'm using too. And it just works across the board. So I'm very curious to hear.
Yeah. So hopefully, when I was here in December, late December, and we talked about the muzzle tuners and whatnot, I was struck by your insistence that changing the powder changes group size. Like, I didn't really understand that, and
I still don't.
Hopefully this will help enlighten some people why it might be occurring. But a lot of years ago, I was on a business trip to Minnesota, and I happened to run into Alan Servin. Do you know who Alan Servin is? All right. So he at the time was a salesman for Hercules powder. There's no longer Hercules powder.
Nope.
And over beers, we're talking about, well, at the time I was like, well, powder's just a push, as long as the powder burns out and you hit the right peak pressure and you got the velocity you want and you got reasonable muzzle velocity standard deviation, how different could it be? And that was my take on life with powders up until a couple of weeks ago. Okay. So that, it just shows you're never too old to learn something. So you guys graciously provided me with some data on some different powder types with a particular bullet. And so I just started, let me dive into this. And the first thing I had to do was to match the powder performance. We got that done. I got a pretty good agreement between the measured and the predicted pressure time behavior. Like, okay, fine. So then I said, okay, once we got that hurdle cleared, now it's time to dive into what powders you're using, and what sort of pressure time history do they provide, and what's the velocity variability? What's all that look like? And then I put that information into the balloting code and said, okay, is this going to tell me anything? And so, okay, yeah, we get dispersion information out of it, which is good information, but that's not the whole story. I then said, what if we looked at the exit states? What the ballistics guys would say the exit states are. It's the angular rate, how much wobble does the bullet have, and then the cross velocity. And the cross velocity comes from like 3 different sources. The first is the CG offset times the spin. And you go read McCoy, and that's, that comes with the bullet being tipped in the bore. Well, there's also the barrel translating sideways. That's a cross velocity. And then the bullet pointing changing is also a cross velocity. So there's those 3 sources that can add or subtract from the wobble part. Like, okay, great. So I ran the 3 different powders. It was H4350, Varget, Hybrid 100V, and I asked you guys to do some shooting with the W760.
Mm-hmm.
And you provided that data. Like, okay, let's go look at it. Well, here are what I'm calling the exit state structural response maps for those 4 powders.
All right. Yeah.
Okay.
Explain what we're looking at
and
here.
So the blue dots are the angular rates.
Okay.
Okay. And all of these graphs, the blue dots are the angular rates. The orange dots are the cross velocities.
Okay.
Okay. So here's H4350, and the muzzle velocity variability is 8 feet per second. The H100V, muzzle velocity variability was 10 feet a second. And you can see that this is very strange behavior, I think. And the horizontal axis, 0 is the average muzzle velocity. And we have plus and minus 1, 2, and 3 standard deviations in terms of velocity.
Okay.
Okay. So that's what we're looking at. And down here we have the 760. And over here we have Varget. And now Varget's got a really low velocity standard deviation. And so this kind of behavior with the angular rate part, if you compare it, say, to the H4350, not so different, but remember that this muzzle velocity variability is half of what this one is.
Mm-hmm.
So, okay, something unique there.
And how many shots per test was that? Was it 100?
How many to get the 4 foot per second?
Yeah.
I don't know.
Probably at least 20s. I don't know for sure. I'd have to look back through it.
Yeah. So the balloting, I did the balloting simulation, captured all of the exit states and plotted them up. And normally the balloting simulation, I get 500 shots. Well, for this study, I decided, you know what, I'm going to double up on them. So each one got run twice.
Okay.
So these are 1,000 exit states for each of these powders. And, you could see where if you just went in and you selected, say, 3-shot groups or something.
Oh, yeah.
You don't know what you're going to get beforehand and what the exit states are going to be. So it's really easy to see, the 4350 here. If you happen to shoot down in here, you've got very low angular rates coming out. Over in here, if you shot, 1.5 times, you might not be happy with that.
Right.
So if you're doing the scanning thing,
of load development.
Development with 3-shot groups, like 5-shot groups. I do 5-shot groups. I'm going to have to rethink what I do.
I'm going to maybe 5-shot groups and then do an aggregate.
Well, but you want to be able to do this without burning the barrel up.
Sure.
We've got to do some more thinking on the topic. But the response here in the H100V, the H100V, by the way, is a unique propellant in that there's a ball powder component and an extruded component. And when I do the interior ballistic simulation, I have to put both of those components in the interior ballistic simulation because the rate at which the propellant is consumed is different because of the geometry.
Sure. So
this is a very, very strange behavior. It's at 0.5 sigma, you have possibility to launch a bullet with 15 or 18 radians a second initial angular rate, which is a big number for this world. Or you might launch it at 8. Big difference, right?
Mm-hmm.
Big difference.
So for the viewer, both those orange dots and the blue dots, the higher those are on the graph, that's bad. You want those numbers to be as small as possible.
Yep.
So again, the blue dots are bullet wobble for the simple term. The orange dots are think of it as the left or right motion path that the bullet is on. You can think of it like that.
Yeah. So yeah, exactly. So you want these guys to be as small and consistent as possible across the whole spectrum.
Yes.
Yeah, I'm kind of impressed with what Winchester 760 did despite the larger velocity spread.
Yeah.
That's what my old man used in the 22-250 years ago. The metal can. They probably still sitting in the basement.
Yeah.
So kind of once you've got that sort of thing, you've got it in your head. Okay, I can plot a response map, an exit state structural response map for the bullet barrel system, and these maps are unique for the bullet barrel, the barrel constraints, the initial conditions, and the propellant. So there's a lot here. Okay, so like, can you stick a line in the sand and say, if I'm going to use this bullet, I'm going to use this powder? I'm not there yet.
No. We talked a little bit when we met up this morning that this is really cool for me to see because this is a simulation that replicates what we have observed over and over and over and over again, which is, and you've heard Miles and Jacob and all of us technical guys talk about it, that the performance you get is a combination of barrel, propellant, and bullet. Mm-hmm. And if you change any one of those three, you're going to get a change in the result. And the easiest one to change is usually either powder or bullet. Usually powder, because you have a lot of options there and you have a bullet that you want to shoot. So this is really cool because it's essentially a verification of that data. And to your point, Jeff, can you make a statement that I'm going to pick these components and it's going to give me this result? No, you can't. And that's what these graphs are showing you, is that even propellants, many of the viewers or listeners are going to see 4350 and Varget on the screen, and they're going to be like, yeah, those two produce awesome results. And some users are going to see 760 and say, I've tried it, but it didn't give me the best dispersion.
It's because of the barrel.
Yes, it's
because of the barrel.
Each of those unique components gives you a different result.
Mm-hmm.
So I had the opportunity to play with a little bit of the variables with bullet barrel interaction. So in addition to the powders, I also played with, like, where do you hold the barrel? Mm-hmm. Do you hold it at the chamber end or do you hold it mid barrel, like your accuracy fixtures?
Right.
Well, it turns out that, you hold them in the middle of the barrel, they shoot pretty good. Go figure. So, there's a lot of, now that we understand this a little bit better, there's a lot more investigation that can be done, and hopefully it'll lead someplace.
Yeah.
So So one of the things of personal interest here was, well, okay, let's compare the CX versus the ELDM. Like, what do the response maps look like? So over here on this series of graphs, we have the ELDM on the left side, the CX on the right side, and two different bore variations, 2 10,000ths. Again, the simple half sine wave
Crookedness,
bore curvature versus half a thou. And you can see as you increase the bore deviation, the bullet response kind of ticks up in some areas.
Yep.
Okay. And it's both factors. It's the angular rate and the cross velocity. And the other thing of interest here, I think, is the fact that when you go from the ELDM to the CX, the response is quite different.
Sure it is.
This is the difference between riding in a Jeep and riding in a Cadillac.
Yes.
It's a very different. It's the CX. The CX is just like your Jeep. I mean, it's a stiff suspension. It's very high vibration frequencies. Like, okay, so, and again, you go from the low bore deviation to the higher bore deviation. You can see these peaks jump right up at you. And before anybody goes into the node discussion, these waves in the response map are, you couldn't pick those out. There's no way for you to say, okay, yeah, I'm gonna load them up and I'm gonna have them exactly the same muzzle velocity every time. You can't do that.
No, because your graphs show the wave response as a function of the muzzle velocity sigma, or standard deviation. And so what that's telling you is within the normal muzzle velocity variation that you can't get away from that wave, that change in response of either cross velocity or angular rate is within that. And so when you're attempting to find it, you might be able to get your average to fall on one of those. However, you're still going to have shots that have a response outside of that valley.
And you're going to believe it's a node.
That's right.
Air quote, node.
Exactly. So then comes the, how did we do on dispersion?
Yeah, that's the real one.
It's where the rubber meets the road.
Mm-hmm.
So for the H4350 and the Varget, I'm declaring victory.
Yeah.
These are pretty good.
Yeah, everything is sub-minute.
Yeah.
Shooting.
Yeah. And for the H100V and the W760, we didn't do so wonderfully. Like, And I've learned over the years that if the stuff doesn't pan out the way you think it should, or the way the simulation says it should, then there's something else going on that the simulation hasn't accounted for.
Yeah. Well, we've witnessed this anecdotally in a lot of testing where it just seems single-based extruded powder works. If you're trying to get small dispersion, there are some situations where we've had spherical powders just not up, both in factory ammo and in just our personal shooting. But I feel like single-based extruded powders, if you had to hang your hat on it, I got 10 barrels and I need it to shoot reasonably well through all of them, you're going to have more sensitivity to the spherical powder than you do the extruded powder.
Yeah, and doing this study, I mean, I didn't include it in the presentation here, but I one of the things I listed was base pressure at exit. Was that the big bugbear of the dispersion? And it turned out that the exit pressure for the for the H4350 was very similar to the other two powders. Varget was the only one that was really substantially lower. And so it doesn't appear that the base pressure by itself can do that, can cause that problem.
Right.
So there's something else going on.
Yeah, more testing.
Yeah. Oh yeah, more testing. Yeah. So another quick breakdown for the viewer there is that the H4350, so blue is the actual test result that we sent over to Jeff, from some testing we did, and orange is the simulation. And those two, they agree quite well with 4350. They agree quite well with Varget. Hybrid 100V, pretty big disagreements.
Yeah.
And then even more so with
that was-
760.
I was quite disappointed with that.
Yeah. So this is obviously a sample size of 2, but with hybrid 100V and 760, you have the addition of nitroglycerin.
Yes. Yeah.
I don't know if that has anything to do with it. Speculation, like I said, sample size 2.
Sure. It is a difference. Yeah.
Yep.
But this is the full answer to this question, is yet to be answered, I guess.
Yeah. There's more things that we need to find out.
That's exciting. That at least, there is nothing new under the sun, but there might be.
There's still rocks to kick over.
Right.
So I think now it's time to talk a little bit about the well, before we leave that, let's talk about the flyers from a balloting perspective.
Okay.
So one of the things, let's go back to the wave plots here. One of the things that I did with the balloting results was I said, okay, is there any correlation between the interior ballistics forcing function draw and large exit angular rate or large cross velocity? Because just intuitively you would say, okay, I've pushed on this bullet a little bit harder. I've got more bounce. I've got more motion of the barrel as a result of that. The correlation between muzzle velocity the sigma, the number that popped out of the Monte Carlo draw, and those large angular rates or cross velocities was tiny. It's not a factor. It's not a factor. So the other thing I looked at was the correlation between the yaw rate and the cross velocity. Again, not well correlated.
Which that's very interesting.
Yeah.
Because you would expect those two to be linked.
McCoy says they're linked.
Okay.
But McCoy's book takes into account only the CG offset and the principal axis tilt, kind of viewed in a pristine environment by themselves, and that the bullet is tipped in bore relative to the bore center line. So this is a little bit, I think, beyond that, and there are extra factors that
gets muddy.
McCoy couldn't take into account.
SnapSafe modular assembly system locks the thick steel exterior together in minutes anywhere in the home. Featuring a pry-resistant 3/16" solid steel door, 8 1-inch chrome steel live locking bolts, digital or mechanical locking options, 9-gauge steel exterior walls, 2300 Fahrenheit 1-hour fire shield protection, fully adjustable shelving, and a lifetime warranty. SnapSafe, a modular safe with welded safe security.
So flyers happen.
Yeah.
Flyers happen. Can we, by using a gain twist, prevent them? I don't know. We'll have to find out.
That'd be really cool if you could.
Yeah.
One way to get rid of flyers is just to shoot smaller group samples.
And omit the ones that don't meet your expectations.
Yeah, so
That's the best
I
way.
can shoot some really good 3 and 5 shot groups with no flyers whatsoever.
Oh, I pulled it. I didn't do my part.
That's
Yep.
right. That's right. Yeah.
Yeah, it must have been that wind I've never heard
That
of.
works every time.
Yeah.
All right.
Before it devolves. Yeah, I'm
So-
excited to talk about this.
So let's do the drag thing. So a long time ago we did this long range test, and from comparing the close in drag variability to the downrange variability, say between Mach 2 and Mach 1.35 or so, you're able to back out what the first max yaw variation is. So as a function of different barrel twists, we were able to come up with some numbers, and kind of gee whiz, as the twist goes up, the variation goes down, and that's due to the increased gyroscopic stability of the bullet. and you've got a certain amount of inbore, quote unquote, inbore clearance or effective inbore clearance as a result of the bullet jumping from the case to the rifling. And that's just part of that deal.
Yep. Interesting. I'm guessing, just looking at this, where you started with a 1 in 12 twist and went down to 1 in 8, was this in 308, like standard 30 caliber?
Exactly. Yep. Exactly.
That is interesting. And the tough part is, okay, so if the drag variation goes down with the faster twist and you're as fast as 1 in 8, that can exacerbate the out of balance tire that we've talked about with CG offset with the bullet. So although you might be able to influence the drag, you might make your dispersion worse by spinning the bullet too fast.
And interestingly, with the fast twist guns, the standard rifling barrels shot worse dispersion than the polygonal barrels, which was a bit of a surprise.
That's interesting. So polygonal rifling, that's kind of maybe
well, those particular barrels, I won't say cheated, but they crowded the low side on the land diameter dimension.
Sure.
So that
could be why.
That helps certainly keep the bullet inbore angle smaller.
Yeah.
Like, okay, that works.
Yeah. So we just recently came out publicly with drag variability reduction technology, which is a geometry that we use to reduce drag variation. So you could enhance that, I guess, by a slightly faster twist rate.
Kind of like this?
Yeah, there you go.
Okay, so this is drag variation versus Mach number, and this is from a fairly extensive test with products from other bullet makers. Okay. And so, the Hornady is the red line.
That looks good.
I took care to make sure it was red.
Yeah, right.
Okay. And I mean, and you can see kind of early on, it's the lowest. That's a good thing. That's important to shooting small groups because it means there's less wobble at muzzle exit. Okay. Comes up a little bit, and then the other thing is these transitions subsonically or transonically, everybody gets them, and it's because the drag versus Mach number is changing rapidly there. And what happens to one bullet, not quite is the same thing happening in the other bullet. And since the slope is steep there, you're very sensitive to it.
And the shape of the bullet has a dramatic impact on what those curves are going to look like.
Yeah, so one of the things I have a note here to talk to you about on that is the drag variability. I mean, in the spark range, for bullets made with a CNC lathe put into sabots, so there's no damaging of the bullet by the rifling. The shot-to-shot drag variability, now sample sizes are smaller because you don't fire typically 30 shots of one configuration through the spark range.
Yeah, data reduction's a lot.
Yeah. So the shot-to-shot drag variability for those samples, if you got between 0.5% and 0.75%, you're doing pretty well. That's kind of, it's my opinion anyway, that you can't easily get below that.
So, even in a perfect scenario,
you're looking
at 0.5%.
Yeah,
because what everything you're looking at here is the shape drag of the bullet. So the point of Jeff's statement is with a bullet launched with a sabot where there's no rifling engraving material off of it, you can't have any shape difference of the bullet shot to shot, even from rifling, right? Like it's the same shape bullet, and they're turned on a CNC.
Yeah, and I need to point out here that the drag variability that I show here on this graph is there's both tipped bullets and untipped bullets in here. And then this test was done in 2016, I think was before you incorporated the DVRT technology.
Yep.
So it's probably better than this.
Yeah, it should be, yeah.
Yeah, right on. That's interesting. And it's neat to see the correlation in the the ways that you can manipulate this stuff. Because in that testing in 2016, we weren't even aware. I mean, we were aware that it existed, but how can you control it was always nobody really knows. And now just to see in that short amount of time, 8 years, how fast the industry changes and how fast the testing methodology changes and how you can just discover things and make them better and better and better and better and better. Yeah. It's just wild.
Okay. And then subsonically, if you're shooting long range, the thing that you worry about is what is the limit cycle yaw? In other words, there's a difference between zero yaw drag, which is what I've shown you just previously, and the total drag. So the zero yaw drag is the drag that you get when the bullet's flying at zero angle of attack. The total yaw is what you get when you do the radar data extraction. Because if the bullet is exhibiting a dynamic instability, it's flying with a small couple of degree limit cycle. What you measure is the total drag.
Yep.
Okay. So this is the same test. Couple of Hornady products, brand X, Y, and Z, and we show the limit cycles. And your product is right in there,
right?
Yep. And then for the ELDM, the 208 grain ELDM, it's the best.
It's significantly lower.
That's interesting. Yeah, significantly lower.
But it's cool to see some outside data that supports what we had measured internally.
Yep. Well, and I'm sure this will get brought up in the comments, and we've addressed it on a podcast. But your Transonic gremlins.
Yeah. So Jeff, there's a large part of the competitive long range shooting community that grows concerned when their bullet is starting into transition or starting into transonic flight.
Yeah.
And typically it's the I call it a gremlin because little mystical creature.
Well, it is a mystical creature, and when your bullet starts to go transonic, it appears, and then it like spits on the bullet and slaps it around, and that's why it doesn't hit where you think it should.
So yeah, when you get an impact that is outside of your expectations, they say that the bullet's it's in transonic, so it's dynamically unstable and there's problems. I trace that back to because that started to be used in the era of BC, right? Nobody's using CD versus Mach, nobody's using the more advanced methods. It's all in BC, and it just so happens that any of your mismatch in your drag curve shapes, although it may happen right at the muzzle, the damage done by that is not observed on target at the muzzle. The damage done there continues to be in effect downrange, and where you start to see those mismatch in drag curves show themselves from a point of impact standpoint is downrange, typically associated with ranges where the bullet's in transonic. So there's been this like confirmation bias association that's happened. And so when guys get a result that is outside of their expectations at those distances, a lot of times they get concerned with it. And my point's been, we've recorded I don't know how many hundreds of thousands of shots on the radar, and have we seen a bullet do that on radar? Yes. But is it common? No.
Because you've seen it like twice out of well over 200,000 shots.
Sure.
That's pretty bizarre. And it is funny.
Not that the limit cycle yaw is increasing in that period of flight. Sure. But is it catastrophic to the point where you start to get wild flyers on target, right? You're shooting at 1200 and you get one that goes 4 mils left. I don't think so.
Well, what's the interesting part there that we've documented and seen, if you have a bullet and it's in Ford off and you're shooting it into transonic, Ford off will tell you where your bullet's going to go. So you can accurately engage targets. Granted, your dispersion at 13, 14, 1500 yards is, that's probably in and of itself. But if you're shooting 2-minute targets, Ford off will tell you where it's going to go, and it will do it with surprising consistency from shot to shot to shot to shot to shot. And I think that's, like you mentioned, those older BC-based calculators, the BC is changing so rapidly, and any mismatch you had at the muzzle multiplied by 2 seconds of flight time, you're in no man's land on your first shot. And I just, it's been remarkable to see Fordoff just tell you where it's going to go and then have people, no, there's no way. Yeah, okay, whatever.
Yeah. So more than a few years ago, one of my colleagues had an opportunity to do some radar data reduction on some 7.62 bullets that were fired at a very long range and tracked with a very high power radar, like to, I can't even tell you the distances.
Multiple second time of flight.
Time of second in the 6 to 8 seconds.
Yeah.
Before they lost signal. It was a tracker head. And one of the things that occasionally happened was a significant uptick in drag. And it happened frequently enough that we didn't feel that it was likely to be something aerodynamic. It was dynamic.
Mm-hmm.
In other words, it was our opinion that the heat input from firing, the interface with the rifling, that heat soaked through the jacket of the bullet and eventually melted the core of the jacket. So now you've got you can call it a moving parts dynamic instability. But you had to be a long, and this was a military bullet, so there was other issues there. But by the time that showed its ugly head, you were well out of the effective, useful range for that bullet.
Yeah.
Like, okay, fine. So, I mean, can things happen? Yeah. I wouldn't be hanging my hat on that one.
Right.
Interesting.
That's what I got, guys.
Jeff, thanks for bringing the PowerPoint, because I know anytime that we have you on the podcast, it always gets technical, and this is going to help. And I'll do an intro at the beginning of the podcast to let the listeners know, if you can, check this one out.
Yeah, the response maps for the different powders just kind of blew me away totally. And so I'm like, I gotta rethink this whole load development thing.
Yeah. We got a podcast about it. You should check it out. It was that you and Miles?
I wasn't on that one.
Okay. Well, it was definitely Miles. Anything else that you want to leave our listeners with, or talk about any of the topics we talked about today?
I'm good. Thank you again.
Absolutely.
I just think it's so cool that a guy that's been in ballistics how many years, if you want to admit it?
45 years.
Yeah, is still learning.
And still motivated to learn, and gets a small little itch of, that doesn't look like what I thought it would look like, and now you're down the rabbit hole.
How do I know it's 45 years? We just celebrated our 45th anniversary.
Well, congratulations.
Yes, congratulations. That's great.
Yeah, awesome. Well, Jayden, thanks for coming on the show. Jeff, again, thanks a million for stopping by, and we can't wait to have you on another one.
Thanks very much. Appreciate it.
Yeah. Ladies and gentlemen, thanks for tuning in to this episode with Jeff Siewert. If you have some topics that you want Jeff to cover on our podcast, please drop them in the comments. We hope you enjoyed it. We'll catch you on the next one.